The topic of this lesson is systematic savings accounts. Let's take a look at example 1. Gary and Ann want to make monthly deposits of $400 into a savings account which offers a 1.95% interest compounded monthly. How long will it take for the account balance to grow to $10,000? The first thing we need to ask ourselves is which form of our compound interest formulas do we need to use? Is this a single deposit that Gary and Ann are making and want to see it grow over time? Or is this a periodic deposit? Now, when we look closely at this problem, we can see that it says it's being compounded monthly. Therefore, we know that this is going to be the periodic interest formula, which is B is equal to P times the quantity, 1 plus R over N, all raised to the power of N times T, minus 1, all over R over N. And remember, B is the balance, P is the principal, R is the interest rate, N is the compounding frequency, and T is time. So what we need to do is we need to identify what each of our variables are. So if we look here, we can see that our principal, or amount being deposited, is $400. So that's our P. We can see that our interest rate is a 1.95. That's our R. But do remember, when we plug this in, we must plug in the decimal form. We can see that it is being compounded monthly. So that is our compounding frequency, and that's our N. And we can see that we do not know our time. However, we do know that we want our balance to grow to $10,000. Let me use a different color for that actually. $10,000, and that is our balance. So the only variable we don't know is T. So that's what we're going to be solving for. And we can tell because here it says how long. So let's go ahead and let's plug in all the information that's been given. So we have 10,000 is equal to 400 times 1 plus 0.195 over 12 to the power of 12t minus 1 all over 0.0195 over 12. Now this looks crazy complicated. It's not as complicated as it looks. So the first thing I think we should do is let's simplify this piece and this piece just to condense this formula. So we're going to grab a calculator and let's start with that part in the parentheses in the numerator. So I'm going to do 1 plus 0.0195 over 12. Now do note, because I'm using a scientific calculator on the computer, it will follow order of operations. Please make sure whatever calculator you're using, it does do order of operations. All right, so I can see that that part here at the top is going to be 1.001625. Now I could round this and just say, oh, it's about 1, or it's about 1.002. I'm going to avoid rounding only because the less I round, the more accurate my final answer is going to be, and also because I'm not super bothered by the length of this number. So I'm going to use this full number. And then the denominator is 0.0195 over 12. And the same thing here. I'm going to write that down, but I'm not going to round it. Okay, so that changes what we had to this somewhat simpler formula. Now, I'm not a big fan of having this decimal here in the denominator. So in order to get rid of this divide by 0.001625, I'm going to multiply both sides of the equation by that. Now, what does that do for me? Well, on the right-hand side, they cancel. On the left-hand side, I'm simply going to multiply. So let's go ahead and calculate again. So on the left-hand side, I have that 0.001625 times 10,000, and that's going to give me a 16.25. So now I have 16.25 is equal to 400 times the quantity of 1.001625 to the power of 12t minus 1. And you'll notice that as I move along, this equation is getting simpler and simpler. Now I notice here that I have this 400 in front of the parentheses. Now that means that 400 is being multiplied, and I want to remove that because remember the goal is to remove as many things as possible working backwards. So I'm going to divide both sides of this equation by 400. Now, why would I do that? Because, well, on the right side, 400 divided by 400 is 1, so they cancel. And then on the left-hand side, let's use our calculator again. We have 16.25 divided by 400. That gives me a 0.040625. And once again, I'm not going around here simply because the number is not super long, and I want to get as precise of a final answer as I can. So I'm going to put that 0.040625 and is equal to 1.001625 to the power of 12t minus 1. Okay, now we're going to continue with this process. So I want to get this 1.001625 to the 12t by itself. I see over here I have this minus 1. So I'm going to remove the minus 1 by adding 1 to both sides. And that's going to give me 1.040625 is equal to 1.001625 to the power of 12t. All right, so now we're to the point where we need to use our logarithms. So remember, if we have a variable in the power, the only way to remove this from a power is to use a logarithm, because remember the logarithm is the opposite. So we have two methods. Method 1, where we could take the log base 1.001625, and method 2, where we just take the simple common logarithm, log base 10, or log of both sides. I think that is simpler, so we're going to just go ahead and use that. So I'm going to jump from here to up here, and I'm going to take the log of both sides of this equation. And this is just the common logarithm, or log base 10. Now from there, I remember we have something called the power property, which says that if I take the log of a power, that power just simply jumps out front. So I'm going to rewrite it using that power property. Now this removes that power, and now the variable is accessible to me. So right now when I look at the right-hand side, I see that there's a 12 being multiplied to the t and a log of 1.001625. I would like both of these, the 12 and this log, to be moved away from the t so that I could solve for t. So since they're being multiplied, I'm going to divide on both sides by the 12 times log of 1.001625. And I'm going to do that on both sides to keep the equation balanced. And now on the right-hand side, 12 divided by 12 is 1, and log of 1.001625 divided by log of 1.001625 is also 1, so those cancel. So now I'm just going to use a calculator once again, and I'm going to calculate this. And we're going to see how friendly this is or isn't. So just a quick reminder, when you use this calculator and you do log, it does require you to type in the number first and then hit log. So that's the numerator. I'm going to divide, and then I'm going to put parentheses just to insist that my denominator does what I want. And you'll notice that it's typing in on the calculator, and I could see if it's doing kind of what I want, right? 001625. And it should be following that order of operations. Okay. And then I'm going to hit equals and see what it gives me. And it's saying about 2 years, 2.0437 years. I'm going to write out a few digits. 2.0437812, which is about 2 years, right? Just slightly over 2 years. Probably at this point, not even a full month. I mean, let's check. So we know there are 12 months in a year. A 0.04, yeah, is like half a month. So about 2.5 months. So Gary and Ann will need to save for a little more than 2 years to grow their account to $10,000. We could get crazy specific and, like I said, figure out the exact number of days, right? There are 365 days in a year. 0.0437812 of that would be about 16 days. So we could say 2 years and 16 days. However, because this is being compounded monthly, I would argue that we would have to just go up to the next month. So 2 years and 1 month. And that's it. All right, now it's your turn to give it a try. Phyllis has opened up a systematic savings account into which she deposits $200 per month, compounded monthly, at a rate of a 1.26%. How long will it take for her account to reach $5,000? Round your answer to the nearest 1/10 of a year. Okay, submit your answer to me on Microsoft Teams for feedback, and then submit your notes and work on Canvas for credit. All right, once you've finished that, go ahead and give yourself a little more practice. Go into the financial algebra textbook, page 137, complete questions 10 and 11.